Hello everyone, I'm Sun Wenting from Hunan University. Today I will share our work with peers through this virtual meeting. The topic of the presentation is Pollutant tax levels and environmental efficiencies in China, a non-convex mid-frontier DEA with natural and managerial responsibility analysis. Our content includes these 5 parts. First, I will introduce what's the research question of the work. We are concerned about such a new social background. To strengthen the control of environmental pollution and promote sustainable development, China officially implemented the Environmental Protection Tax Law. It recognized the conversion from pollutant discharge fees to environmental taxes on January 1, 2018. Although the standards for solid waste and noise pollution are the same across the country, different tax levels are imposed on air and water pollutants in different regions. Take Beijing and Anhui as examples. In the left picture, air pollutants in Beijing are 12 yuan per pollution equivalent and 1.2 yuan in Anhui. In the right picture, Beijing's wastewater is 40 yuan per pollution equivalent, which is much higher than the 1.4 yuan in Anhui. The picture reflects the different levels of emission reduction pressure in various regions. Environmental efficiency evaluation can show the role of management measures in environmental protection and social and economic development. In this social situation, a new research topic is to evaluate the environmental efficiency of the various regions in China and the different pollutant tax levels. However, most traditional methods cannot reflect the pollutant tax levels. Therefore, a research question arises: how to measure the region environmental efficiency? We began to find solutions from previous studies. In the first step, we learned that DEA, data development analysis, can handle multiple inputs, multiple outputs, as well as undesirable output. Therefore, it has a wide range of applications in energy and environmental efficiency research. However, the traditional DEA usually ignores the differences in the technical environment of the evaluation unit, that is heterogeneity. An important concept in heterogeneity is environmental variables. Based on the traditional CCR and the BCC model, Banker and Morrow was the first to establish a DEA model that includes environmental variables. In most existing studies, environmental variables are used to group DMUs. However, the disadvantage of this direct group evaluation is that if the number of DMUs in a group is limited, the evaluation result may be meaningless. Besides, the evaluation of DMUs from one group is independent of the other group. Therefore, the evaluation results are not comparable between the groups. To solve this problem, some researchers introduced a new concept, the metal production function. According to their research, the frontiers of all achievable production possibilities are defined as the middle frontier of all units. It not only solves the DMU's number problem we just discussed, but also analyze the connection between the groups and the whole. At present, there are two types of mid-frontier model constructions, convex and non-convex. The latter believes that although the frontier of each group is convex, the mid-frontier that defines the unit of those groups is not convex. I will explain the details in the method section. Also, environmental efficiency assessment will naturally have undesirable outputs such as waste gas and wastewater. Many researchers have completed research on undesirable output, in particular the DDF, directional distance function, which is one of the most widely used methods at present. In addition, for input, Susie and Goto first proposed two concepts related to input in 2012. Among them, natural disposability means traditional inputs such as energy, labor, and so on, while management disposability means increased inputs such as technological innovation, special funds, advanced equipment to reduce undesirable output. At present, a series of more in-depth studies are underway. In summary, our study aims to assess the environmental efficiencies of China's provincial administrative regions by applying the non-convex mid-frontier model as well as natural and managerial disposability. So, the second part, how to do the method. In Figure 1, we first illustrate the differences between the group frontier, convex and non-convex mid-frontier. Suppose there are 15 DMUs from 3 different environments of A, B, and C. Taking B5 as an example. By referring to its own group, the input inefficiency is reflected in GB5. The DEA frontier under the convex exception is the share of all DMUs, namely A1 to 3, C3 to 5. In this case, the inefficient value is MB5. As a non-convex exception, the mid-frontier is the combination of the boundary of each group. It consists of 3 parts. The 4 inefficiency here is NB5. Why we choose the mid-frontier and the non-convex exception? It is because the mid-frontier is a unique concept, and there is no A3 to C3, the right line part, which is a convex combination of multiple technological environments. Besides, on the right is the PPS of the mid-front and the convex and non-convex exceptions. Then, the non-convex mid-frontier is dominated. Model 5 uses the input-oriented radial measure, which can directly determine the efficient value of the DMU to be evaluated and the effective frontier of each group. The efficiency value of the non-convex mid-frontier is the smallest among those of all groups. Considering the better analysis of undesirable output, Model 6 is formulated under the DDF, where represents the final efficiency value of the DMU to be evaluated and the mid-frontier. Finally, subtract 1 from it and get an efficiency value of the non-convex mid-frontier. Combined with the natural and managerial responsibility, we finally get the model 12. Among them, the red box harness management input. Subsequently, we conducted an empirical analysis. The input indicators such as manpower, material resource, and financial resource are selected. GDP is the desirable output, and West gas and West water are undesirable output. And we first classify the 31 provincial administrative regions into 3 groups: high, middle, and low, based on the Pollutant tax level. Then we calculate the environmental efficiency of each region. Figure 2 shows the results of environmental emphasis assessments. From the clockwise direction of the left picture A, it can be concluded that the emphasis results of the 5 regions from Beijing to Henan are consistent in 4 different situations. From Shanghai to Hainan, there are few differences between those 7 regions. For the last 19 regions from Guangdong to Yunnan, the emphasis differences are significant. Besides, the small graphs B and C in the upper right corner indicate that the 2 mid-frontier emphasis results lines and the non-convex exception includes the line and the convex. This is also consistent with the ultra situation, because under the convex, the frontier of DEA will expand outward and will include the virtual combination of DMUs between the 2 groups. So, the emphasis value will be underestimated when referring to the benchmark. It also reflects that the emphasis value line will be closer to the center of the circle in the graph. Table 4 shows the reference benchmarks and weights of infective regions. In several, if there are benchmarks built by DMUs in different environments, the convex exception of the mid-frontier in DMU heterogeneity may lead to unrealistic results. For example, in Hunan, according to the convex exception, the reference units of weights are Tibet, Jiangsu, and Shanghai. However, those 3 regions have different tax levels. The combined virtual combination cannot be used as a reference for efficiency improvement in Hunan in practice. According to the non-convex exception, Hunan refers to Tianjin and Jiangsu. The 2 are at the same tax level, both of which come from the first group. This shows that after increasing the pro-tax tax level in Hunan, it can also refer to the first group of benchmarks and improve environmental efficiency. To further analyze the traditional natural input and the currently encouraged management input, we first use the non-convex mid-frontier without management input model, and the results are shown in Table 5. Comparing the emphases and the mid-frontier and its group frontier, the emphases of the second group with 1 province and the third group with 3 regions are overestimated in the groups shown with 1.00. In the next column, we list the MTR scores for each region, showing the gap between the mid-frontier and the group frontier. The comparison includes management input, and the results are shown in Table 6. Besides, we have overturned some regions with large changes in rankings. For example, in Guangxi, Liaoning, and Xinjiang, those regions have seen great declines due to insufficient government investment in environmental protection. This shows that those regions should pay close attention to environmental protection funds in response to the country's sustainable development strategy. Conversely, in Anhui and Inner Mongolia, the rankings of those regions have risen because of the government's increased investment in environmental protection. Finally, the conclusion. Comparing the text level grouping, the analysis overturned the research results of the improvement direction of inefficient regions. List the 3 highlights of our research. Number 1, grouped by pollution text level. Number 2, consider the natural inputs and the managerial inputs. Number 3, use the non-convex mid-frontier. Here are some more references. Okay, that's all. Thank you for your attention. If you have any question regarding today's presentation, please do not hesitate to contact me by this email. I really appreciate your time. Thank you very much.